Welcome students. In this video session, I am going to discuss about syntax directed definition. So, syntax directed definition is nothing but the context free grammar along with semantic rules. So, in this syntax directed definition, we will be having the context free grammar, and in the context free grammar, for every production, we will be having a set of semantic rules associated with it. And the symbols whatever we have in the grammar, we will be having some attributes associated with it. So syntax data definition is nothing but grammar along with semantic rules. For every production in the grammar, we will be having some set of rules associated with it, and for all, every symbols what we have in that grammar, we will be having some attributes associated with it. So this is what syntax data definition. Now let us discuss with some examples. So assume that we have a production we have a production E tends to E1 plus T. Now this is a production in the grammar, and for this production we have a semantic rule like E dot val equal to E1 dot val plus T dot val. Now this is what called as syntax directed definition. And one important point is that here E and E1 are the same. Okay, so just to differentiate that it is a left side of the production and the E in the right side of the production, we have added one uh, for the E. Okay, so both E and E1 are same. So E dot val equal to E1 dot val plus T dot val. So this is a rule associated with this production. Now we already learned what is parse tree in our earlier classes. So whenever we have an input string and we want to validate that input string is with correct format, we will be constructing parse tree. Using the grammar, we will be constructing the parse tree for validating the input string. So we know already what is a parse tree is. Now there is something called annotated parse tree or decorated parse tree. So annotated parse tree means in the parse tree, in every node we will be having the attributes along with the symbols. Now as an example, just see here E dot val is being expanded like E dot val plus T dot val. Now usually in parse tree what we're doing, we will be just expressing like E1 expanded to E1 plus T. This is how we will be having it in parse tree. But in annotated parse tree, along with the symbol, you will be also representing the attributes. Now in this case, val is an attribute. Now there are two types of attributes in syntax related definition. One is synthesis attribute and another one is inherited attribute. Synthesis attribute means we will be evaluating the value of synthesis attribute by referring its child node. A very good example is what we have seen in our earlier slide. So here we will be evaluating the value of E dot val by referring its child node E dot val and T dot val, because the rule is given like that. The value of this E dot val is equal to E1 dot val plus T dot val. So we are computing the value of this node by referring the value of its child node. So E dot the attribute val can be called as a synthesis attribute. And there is something called inherited attribute, in which we will be evaluating the value of the particular attribute by referring either its parent node or by referring its sibling node. Okay, so these are the two attributes. Now let us discuss with some examples about these two type of attributes. So first let's discuss about a synthesis attribute. I have a grammar, and for every production I have a semantic rule associated with it. Now for the input string 4 star 5 plus 6, we'll be having an parse tree. We are just considering the parse tree. Hope everyone can uh, get the meaning of it. Okay, so how we have considered the parse tree. So initially from the starting symbol, we have expanded to E, then E is expanded to E plus T. By referring this production, you are just expanding it. Then again again this E is being expanded to T. That is what happened here. Then T is expanded to T star F. Then T again expanded to F, and F again expanded to digit. Okay. So similarly this side, T is expanded to F, and F is expanded to digit. So by referring this grammar only, by referring this production rule only, we have expanded this. And similarly here also, uh, T you have, so T again it can be expanded to F. That is what happened here. Then again from F it is expanded to digit. Now this parse tree is matching with the input string 4 star 5 plus 6, right? So here for this digit we'll be having 4 star, again here 5 plus 6. So we will be coming to a conclusion that this input string is in correct format. Okay, fine, that's well and good. Now let us come back to annotated parse tree. What is annotated parse tree? In every node, in every interior node, wherever you have the symbols, you will be having the attributes. Now in our case, we have the attribute called val for the symbol E and also for the symbol T and F. Okay, now let us see how we are going to compute the value. So if you want the value of E dot val, okay, so how you can calculate the value of this E dot val? You have to refer the production. So here E dot val is been expanded to E1 plus T. So this node is been expanded to E plus T. Okay, so you have to refer this production rule. You have to refer this semantic rule. So what this rule says, E dot val equal to E1 dot val plus T dot val. So for the computing of value of this particular node, you want to know the value of E dot val and also T dot val. Only by adding these two values, you can know the value of E dot val. So for computing this, we need the value of its child node. So it is an synthesis attribute. Now let us try to find the value. So now we are in the conclusion that we need the value of E dot val and also T dot val. So let us compute that first. So here we have E dot val. So what is the value of E dot val? How to calculate the value of E dot val? So here E is been expanded to T here. So E dot val equal to T dot val. Again you want to know the value of T dot val. Again you are just going here. So T dot val is equal to T1 dot val star F dot val. So for computing the value of this attribute, you need the value of these two things. So you are just going to T dot val. So T dot val is T is expanded to F. So T dot val is equal to F dot val. So only if you know the value of F dot val, it can be assigned to T dot val. That is what the rule says. T dot val equal to F dot val. Right? So now you want to know the value of F dot val. So F dot val is nothing but F dot val is equal to digit dot lex val. So you'll be getting the value from lexical analyzer. So what happens? Now F dot val will be taking the value 4 because in our input string the first input is 4. So it will be taking 4. So once if you know the value of 4, so that value will be assigned to F dot val. So now F dot val will be 4. Next what happens? Now you know the value of F dot val. Now since you know the value of F dot val, it can be assigned to T dot val. That is what happened next. Now similarly, you want to know the value of F dot val here in this right side. So if you want to know it, you want to go to digit dot lex val. So in our case, it will be 5. So F dot val will be 5. Now you know the value of T dot val and also F dot val. when you apply this rule, what happens? The T dot val will take the value 20. Okay, so T dot val is 20. So whatever T dot val has, that will be the value of E dot val, because the rule is like that. So 20 will be assigned to E dot val. Now you computed the value of E dot val. Similarly, you have to compute the value of T dot val. So we'll be just going to leaf node. So digit dot lex val equal to 6 in our input string. The last input is 6. So digit dot lex val will take the value 6. F dot val will take the value 6. Then T dot value will be also 6. Now you know the value of E dot val and also T dot val. Now what happens? Here what's the rule? E dot val is equal to E1 dot val plus T dot val. So the value is 26. The reason why we discuss this particular example is this is synthesis attribute. The val attribute is called as synthesis attribute. Why it is called as synthesis attribute? Because we can evaluate the value of the synthesis attribute by referring its child node. Here we computed by referring the child node lex val. Here we computed the computed the value of this val by referring the f dot val. Similarly, here also we have computed the value of E dot val by referring the child node E dot val and also T dot val. So since we are evaluating the value by referring its child node, it is called as synthesis attribute. Now next, let us discuss about inherited attribute. So, so what is inherited attribute? In inherited attribute, we will be evaluating the value of the attribute by referring its parent node or by referring its sibling node. Now let us discuss some example. Now I have an input string int a comma c. It's a declaration statement, and I have a grammar for it. Now for this input string, if you construct the parse tree will be like this. So initially the starting symbol is s, and s will be expanded to tl. Then L will be expanded to T will be expanded to int. Okay, T will be expanded to int. Then L will be expanded to L comma ID. L comma ID, because we should expand it in such a way that it is matching with the input string. Okay, since we have two variables declared here, again you are just using this production L tends to L1 comma ID. Okay, now it will be matching. So here it will be taking, when you compare with your input string, this node T will be taking the value int, L will be A, and here it will be C. Now this is a parse tree. Now let us compute the value of the attributes. Here we have two attributes. One is type attribute, another one is in attribute. Okay, fine. Now let us compute the value of the attributes. First let us compute T dot type. So what is T dot type? So we have expanded T to int, right? So when we expand T to int, then T dot type will be int. We have a rule stating that T dot type equal to int. So T dot type will be int. Now let us try to calculate the value for L dot in. So here L dot in equal to T dot type, because when we have the production S tends to TL, we have a rule stating that L dot in equal to T dot type. So L dot in will be computing the value of L dot in by referring the sibling node T dot type. Are you getting it? So L dot in equal to T dot type. So we are referring the value of its sibling for this. Okay, is it okay? So L dot in, the in attribute is an inherited attribute. Why it is inherited? Because it is, for evaluating its value, it is referring its sibling node. That's why it is inherited attribute. Similarly here also L dot in. So how will you compute the value of L dot in? What production you have used? L tends to L1 comma ID. So here you have a rule L1 dot in equal to L dot in. So here L1 dot in, I already told you L1 L all are same, just to differentiate left side of the production, right side of the production, or parent node, child node, we have just added the subscript one. Both are same actually. So L dot int will be, sorry, L1 dot in will be L dot in. So whatever the parent node has, parent node attribute has, the same value will be in the child node attribute. So L1 dot int equal to int. Okay, so again we are proving that in is an inherited attribute. Already we proved it is an inherited attribute. Again it is been justified. Is it okay? So this is what inherited attribute is. Is it okay, students? Fine. So next we are discussing about dependency graph. Now when we take an annotated parse tree, we'll be having so this attribute in it. We will be having inherited attribute in it. Now, how to evaluate the attributes? Suppose if a node needs a value of another node, then you have to evaluate that particular node first before evaluating this node. Say for example, you want to evaluate the attribute A, but that attribute A needs a value from another node. Okay. Now in this case, the value of B can be evaluated only if that particular node, the node which it refers, that should be evaluated. Only after evaluating that, the node B can be evaluated or the attribute B can be evaluated. Okay, so ultimately the point I am trying to convey is that there should be some order. There should be some order. Okay, so in that order, if we evaluate the attributes, we will be finding the value for all the attributes. Suppose if you're just randomly evaluating it, okay, then we have to try with different possibilities. So to ensure that the nodes are being evaluated in particular order without any difficulties, we are going with dependency graph. So dependency graph is used for finding the evaluation order of the attributes. Once after considering the dependency graph, we will be performing topological sort. So the order in which we are getting, in the order we can evaluate the attributes. If we do so, there will not be any difficulties. So that is what dependency graph is. Now in dependency graph, we will be placing an edge between two nodes. Let us be specific. I am just placing an edge between node A and node B, a directed edge from node A to node B. Once if you place an edge between node A and node B, it means that node B needs a value what node A has. Okay, so when we place an edge between node A to node B, it means that B node needs a value what A node has. Okay, so in such, by following this logic, we will be placing the edges in the dependency graph. Okay, now let us discuss with some examples. So for considering the dependency graph, we have to give two inputs. One input is the parse tree and the second input is the semantic rule. Only using these two inputs, the dependency graph can be constructed. Now let us discuss some examples. I have an input string like real a comma b comma c. A real a comma b comma c, a declaration statement. Now for the statement real a comma b comma c, the parse tree has been connected. In specific, annotated parse tree has been constructed. Now this is how the annotated parse tree will looks like. So we have constructed this by referring the grammar. Okay, by referring this grammar, we have constructed the annotated parse tree. Right. Now let us construct the dependency graph. This is how the dependency graph will be. I'll make the point clear. Now, which node can be evaluated first? Now in this annotated parse tree, the ID1 value can be evaluated first, because it will be taking the value from the lexical analyzer. Okay, so it can be evaluated first. Then we cannot evaluate L dot in, because L dot in our earlier case we have discussed, when we are discussing about inherited attribute, we have discussed it. So L dot in will take the value what its parent has, because the grammar is like that. So we can identify or we can evaluate the ID1, but we cannot proceed with L dot in, because L dot in takes a value from its parent. So we cannot proceed here. Okay, so this is what we are placing an age from 1 to 10. So 10 refers to this node only, but we cannot completely completely process this node, because it needs a value from its parent node. So partially we are just completing it. Okay, fine. So we are placing an edge 1 between 1 and 10. 1 and 10 refers to nodes. Then we are just going to parent node. Even here also you cannot evaluate this. Okay, because it has a child node. Okay, fine. So let us process its child. So ID2. So what is ID2? It will be taking from the lexical analyzer. So second ID2 will be assigned here. So we are placing an edge between 2 to 8. 2 to 8, you are just placing an edge. Now, even this node cannot be processed completely, because L dot in needs a value from the parent node. So you can only come partially can process this. So just placing an edge 2 to 8, again you are just proceeding to parent node. So here also you have ID3, so it means that you can place an edge between 3 and 6. Between 3 and 6, because you can get the value from the lexical analyzer. So from 3 to 6 you are placing an edge. Now can we process this L dot in? No. This L dot in needs a value from its sibling node. Okay, so you cannot process this. Okay, so we have placed an edge from 1 to 10, we have placed an edge from 2 to 8, and we have placed an edge from 3 to 6. Now next what you are doing, we're just proceeding here. So t dot type equal to real. Now you can get the value here, right? Because in our declaration statement we have real here. So t dot type is equal to real. Now you got the value here. Now with this value we can place an edge from this node to this node. From 4 to 5 you can place an edge. Why we are placing in 4 to 5? Because the L dot in is nothing but t dot type. We have a rule like that. L dot in is nothing but t dot type. Okay, so once if you get the value here, then you can place an edge. So from 4 to 5 you can place an edge. Now you got the value here, we got the L dot in value. Now with this what we can do, we can completely process this L dot in. That's why they placed an edge 5 to 6. Now you process this node. Next what we can do, you can go to its child node, L dot in. The child node L dot in is nothing but whatever the parent node has, that will be the value here. So again from 7 to 8 you can place an edge. So it means that you are completely processing L dot in. Then again you are just coming to the next node L dot in. So here also L dot in will take the value whatever its parent has. So L dot in is real here. So this is the same real you can just assign here. Okay. So from 9 to 10 you can place an edge. Now this is how you can construct the dependency graph. Okay, now in this example 5 and 6 refers to the same node, 7 and 8 refers to same node, and also 9 to 10 refers to the same node. Okay, just to differentiate two instances. In one instance it is not been processed completely, in the next instance it is been processed completely. Just to differentiate it, we have two nodes for the same symbol, 5 to 6, 7 to 8, and 9 to 10. Now we have considered the dependency graph. Now how to find the order? Why we are going for dependency graph? Just to know the evolution order we are going for dependency graph. Now we have found the We have considered the dependency graph. Now how to find the evolution order? We have to perform the topological sort. Okay. So one order we will be getting when we perform topological sort is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is one possible order. So when you evaluate the nodes in that order, the elements, you can evaluate the attribute values without any difficulties. So this is what dependency graph is. Then we have two types of syntax directed translation. So syntax directed translation is more or less like syntax directed definition. The only difference is how we are expressing the semantic rules. In syntax directed translation, the semantic rules will be expressed in the form of program fragments. So the syntax or the way how we write the program, in the same way more or less we'll be expressing the semantic rules. But whereas in case of syntax related definition, it will be just expressed it, but we will not be following the syntax what we have in programming language. So syntax related definition and syntax related translation, they both are more or less same. The only difference is in syntax related translation we will be using programming notation for expressing the semantic rule, but whereas in syntax related definition it will be just expressed as it is. There are two types of syntax related translation. One is S attributed syntax related translation, another one is L attributed syntax related translation. S attributed syntax related translation in the sense, in that syntax directed translation we will be having only synthesis attribute. Okay, we will be having only synthesis attribute. But whereas in case of L attributed syntax related translation, we may have synthesis attribute in it, and also we may also have inherited attribute in it. But when we have inherited attribute, we have one additional constraint. The constraint is that we should evaluate the value of inherited attribute either by referring its parent node or its left sibling. I'll repeat the point once again. In L attributed syntax translation, the attribute can take, if it is synthesis attribute, obviously it is going to refer its child node. There won't be any issue with the synthesis attribute. But in case of inherited attribute, it should evaluate the value by referring the parent node or by referring its sibling node, left sibling node. Okay, so this is the constraint we have for L attributed syntax related translation. The next one is syntax tree. So syntax tree is another intermediate representation of the instruction. Earlier we have represented it in different forms, but the next intermediate representation is syntax tree. So how we are going to construct the syntax tree? The syntax tree will be constructed using the parse tree. So we already have parse tree. Only by using the parse tree we are just going to construct the syntax tree. And also we will be having semantic rules also. So only by using the parse tree and also semantic rules we will be evaluating or we will be constructing the syntax tree. Now let us discuss some examples. Now I have a grammar like this. So we have different productions in it. Now for each production we will be having a semantic rule. And how this rule will be, the rule for considering the syntax tree will be different from the rules what we discussed earlier. Okay, so here the rule mainly will be doing two things. One thing is either it may create an interior node or it may create a leaf node. Maximum we will be having only two type of rules. One rule is to create leaf node and another rule is to create the interior node in the syntax tree. Now let us discuss it one by one. Now say for example, for this production, we want to create an interior node. E dot node equal to new node. The operator what we have here, that is the first input, and second input is E1 dot node, and our third input is T dot node. So the next, for the next rule, it is also going to create an interior node, and for the rule E tends to T, for the production E tends to T, we have the rule like E dot node is equal to T dot node. Again, T dot node is equal to E dot node. Suppose in a production, in the right side, if you have an terminal in it, then obviously we will be creating the leaf node. So T dot node is equal to new leaf id comma id dot entry. The next one is T tends to num. It is also a terminal in the right side. So again for this case also we are just creating the leaf node. Right. So now let us discuss with some examples. Assume that we have an input string a minus 4 plus c. A minus 4 plus c. So for that, first we shall construct the parse tree. The parse tree will be like this. By using this grammar only, we have considered the parse tree. E is expanded to E1 plus T. Again, the E is expanded like E minus T. Then E tends to T, and then T tends to ID. So here T tends to num. Similarly, this side T tends to ID. So by using this grammar, we are just evaluating this. We are just validating the input string. Now the input string is a valid string. Now let us consider the syntax tree for this. Now how to consider the syntax tree? By referring this semantic rule, we are going to construct it. Okay. So first what we have to do is we have to travel from leftmost leaf to rightmost leaf. So first leftmost leaf is ID1. So what rule you have applied here? T tends to ID. When you have T tends to ID, what's the thing you have to do? You have to create a new leaf node. That is what we are doing here. P1 is equal to a new node we are just creating, and it has been pointed by the pointer called P1. So P1 is equal to new leaf ID comma entry A. Next what we are doing here, we have created a node because of the production T tends to ID. Next E tends to T. So when you have E tends to T, what the thing you are doing? You're just creating, you're not creating a node, already created node, you're just assigning to E dot node. So already you created a node. Already you created a node, and that reference is available in T dot node. So that reference again you are just assigning to E dot node. Okay, so as of now we created one node. The next one is you're just traveling this. You have to travel along with along the leaf nodes from left to right. Then again you are just going to minus 1. Then you are just not minus 1, it's minus. The next one is T tends to num. So when you have T tends to num, then what you have to do? You have to create a new leaf node. So T dot node is equal to new leaf of num comma 1. You're just creating a new leaf node. Now after creating the leaf node, you're just going to the parent node. It is E tends to E minus T you have applied. So when you have E tends to E minus T, then what you have to do? You want to create a root node. You want to create not root node, you want to create an interior node. So that is what you're doing here. P3 equal to new node. So you're just creating a new interior node. In the first field you have minus, and the second field you have P1 and P2. Then from here you're just moving to the next node plus, you not do anything. Then T tends to ID. So for t tends to id, what you do? You want to create a leaf node. So that is what p4. P4 is equal to new leaf of id, comma the value what you have in id. Then from here you're just going to the root node. It is e tends to, what rule you have applied here? E tends to e1 plus t. So for e tends to e1 plus t, you want to create a new interior node. That is what you're doing here. Once after reaching the root node, you can stop processing the tree. Let's see how the syntax tree looks like. This is how the syntax tree looks like. So this is P1. We created node by P1, and then this is P2, and this is P3. P3 second field pointing to P1, third field pointing to P2. Similarly, root node. Left side you have a reference to the node what we have here. It is P3. On the right side you have the reference. So this is how we have to consider the syntax tree. So there is something called directed acyclic graph. It is very similar to the bit of a parse tree. When I say it is very similar to of syntax tree, it means that so it is also an intermediate representation. Just like syntax tree, parse tree is also an intermediate representation. The only difference is that in syntax tree, for every sub expression, you will be creating a new subtree. You will be creating a new subtree. But whereas in case of directed acyclic graph, we will be creating the subtree only once, and wherever we need it, we will be referring it. Okay, so this is what called as directed acyclic graph. Now, as an example, just see here a plus a star b minus c plus b minus c star b. Now, when we construct the directed acyclic graph, the graph will be looking like this. When you see here, a plus is referring to the a node and also the a node star b minus c. So that is what we have. But instead of having the a twice, we will be having the a only once. This provision is not available in the syntax tree. Here you just see b minus c we have twice. B minus c expression we have it 2 times. But even though we have 2 times, in your directed acyclic graph, it is been represented only once. So this is what called as directed acyclic graph. Okay. Just an example. When we have an expression like I is equal to I1 plus 10, I equal to I1 plus 10. So we are not creating two i's. Whatever I you created earlier, the same ID I is being used further. Okay, and there is something called value number method. So whenever once we consider the directed acyclic graph, every node we can place every node's reference we can place it in an array, and whenever we need any node, you can refer it by means of the array. Now in this case, if you want to refer the node ID, we will be referring the node with value number 1. Similarly, if you need the node plus I, if you want to refer this node, then what you have to do is you have to in the operator field you have 1, and in the second field you have the reference to the left side, and the third field you have the reference to the right side. That is okay. But we will be referring this node by using the value number called 2. The index, normally we will be referring the individual position of our array by using the index value. Similarly, we are accessing the individual elements by using the value number. By using value number only, we will be referring the individual nodes. We can discuss the further topic in our next class. Thank you, students.